we're going to talk about confidence intervals and hypothesis testing, and yes, this is your last lesson. Give yourselves a pat on the backs for making it through the hell that is elementary statistics, but it's not over yet. So when we talk about confidence intervals, first of all, we have to talk about a point estimate. This is the process of estimating unknown population parameters known by sample statistics. It's also defined as the value of a sample statistic used as an estimate. And you'll get a little more perspective on that definition once we get into your homework problems, and I will be doing some examples. But first, before we talk about confidence intervals and hypothesis testing and get all into the math, you need to know what a confidence interval is. It's an estimate of a parameter consisting of an interval based on a point estimate together with a confidence level specifying the probability that the interval contains the parameter. Well, we need to put this in English so you can actually understand. A confidence interval is you do some math and you get a lower bound and an upper bound of how close you are to the actual parameter of the population as opposed to your sample statistics, because there's no point in doing sample statistics if we're not going to draw an inference or a conclusion about the population. So I'm going to give you some symbols and some notation because the next several slides are very symbol heavy. Basically, if you just look at it, you would be, what the hell is this? And have no idea. So I'm going to try and break that down for you. This Greek letter right here, alpha, is a small constant. It's usually between 0 and 0.1. And you'll have 3 alphas that I give you throughout, whether it be 95%, 90%, or 99%, and they correspond to this alpha. And again, I'll make that clearer later. Z alpha over 2 is the standard normal value. Z, the z-score that has the area of alpha over 2 to the right of it. Okay, that's a whole lot of crazy English that makes no sense, but it's really just a number that you're going to need. 1 minus alpha lies in the interval between negative z alpha over 2 and z over 2. And our true population parameter z lies between that interval as well. When we're talking about z intervals or confidence intervals, we're usually doing it for 1 or 2 values, either the mean mu or the population proportion p. They use different formulas, but they're very much the same. It's just different ways of manipulating the numbers. So the z interval for mu may be constructed only when either of the following conditions are met. So either you already know that the population is normal and the problems are going to tell you that, and you know the standard deviation, which they tell us, and the sample size n is larger than 30, and you know the value of the standard deviation. So you need to make sure that you have these 2 qualities before you go into all this other math. So when a random sample size n is taken from a population with a percent confidence, which will either be 90, 95, or 99% confidence interval for mu, is given by these 2 formulas. The mean minus the margin of error and the mean plus the margin of error. The notation is done in parentheses with the lower bound number and the upper bound number. The z alpha over 2, when you have 90% confidence, you need to find the z alpha over 2, and that is going to be 1.645. For 95%, it will be 1.96, and for 99%, it will be 2.576. These are your life, so you should be memorizing this or writing it down somewhere. So let's look at an example to put this in a little bit of perspective. So this is on page 373 of your second edition of the textbook, and it asks that the College Board reports that the scores on the 2010 SAT math test were normally distributed. So there's one of our conditions. We know it's normal. A sample of 25 SAT scores had a mean of 510. Assume that the population standard deviation of such scores is, I forgot to put that in there. Okay, it's the standard deviation is 100. Typo number 2 in these videos. I apologize. I thought I edited them. So what we want to do is we want to construct a 90% confidence interval, and that translates as follows. Our sample size is 25. Okay. 510 is our sample mean. Our standard deviation is 100. Our alpha is 0.10 because we're looking for a 90% confidence interval. So our alpha over 2 is 0.05, and our z alpha over 2 is, according to the chart, 1.645. So now what we do is we plug in to these formulas, and I will do a much more in-depth example in the example videos, but I plugged the numbers in, did the math, and came up with 477.1 and 542.9. So what does that mean? That means I can say that with 90% confidence that the population mean lies between 477.1 and 542.9. When we talk margin of error, that is the z alpha over 2 times the square standard deviation over the square root of the sample size. That's that part of the equation. This is the standard error right here. Okay, so when you were asked to calculate a margin of error, you should already have calculated that. It's 1.645 times 100 over 5, or 1.645 times 20, and whatever that equals. So now when we talk about, we've talked about mu, so the next thing we need to talk about is the population proportion p. The lower bound is defined by p hat, which is our estimate, or our sample mean, minus z alpha over 2, that doesn't change, times the square root of p hat times 1 minus p hat over n. Okay, margin of error is, that is the z alpha over 2 times the p hat times 1 minus p hat over n. And when there are problems that ask us to do sample size, to find the sample size for a given margin of error, we're going to use the central limit theorem for proportions, and I will remind you what that is when we come to an example. So when we don't know p hat, or when we know p hat, the sample size needed to estimate the margin of error is here, but that doesn't make sense because you have the margin of error here. So that's why we need to use the population, the central limit theorem. But when we don't know p hat, this makes it a little easier. So I'm going to stop the video here, and I'm going to run a couple examples on confidence intervals for you before we get into the hypothesis testing portion of this slideshow, because that's a lot more crazy. So stay tuned.